Hello and welcome to this video on the motor effect. This sits alongside our other video on magnetism and electromagnetism. In that we looked at the magnetic fields of permanent magnets and electromagnets. In this video we're going to see that exciting things happen when we combine the two. First of all, we want a permanent magnetic field that is uniform. That means parallel field lines. In the last video we looked at the field of bar magnets, which were far from uniform. They went around in loops. So this time, instead of a bar magnet, we're going to be using these Magnadur slab magnets, where the poles are on the faces rather than the ends. These Lego models compare the two. So our bar magnet is like this, with a north at one end and our south at the other end, whereas our Magnadur, we have the poles on the faces. When I put two Magnadurs down with opposite poles facing, I then get nice parallel field lines running from the North Pole on one to the South Pole on the other. To see the motor effect, we want a current carrying conductor that's running perpendicular to our permanent magnetic field. We also want that conductor to be able to move. There's various ways of showing this. One of the simplest is basically by using just a bit of aluminium kitchen foil and putting that in a circuit, a low voltage supply, and between the yokes of our Magnadur. When I turn the power on, we should see that foil move. Hopefully you saw that kick up. I'll just try it again. You can also see, if we reverse the poles of the magnets, the force on the foil acts in the opposite direction. It goes down. Now, if I swap the direction of the currents, and this time it's moving up. So either reversing the current or reversing the poles changes the direction of the force on the foil. Another way of demonstrating this is with the rolling rod demonstration. So what we've got here is a very simple circuit with some stiff copper wire. So we've got current travelling up here, then we've got a movable bit of copper wire on top, and then current flowing back down this side. So at the moment, if I put a current through that, nothing happens. But when I add the magnetic field perpendicular, so our field is now going upwards, north to south, our current is going towards the camera. Let's see what happens. You can see we got the wire rolled to the left as you're looking at it. Just show you that again. If we reverse the field again, so I've now got the field going downwards. Hopefully you saw the rod roll the other way. So what's going on here? Well, we've got the two magnetic fields combining. First of all, we've got the field from the permanent magnets with the Magnadurs running north to south as shown here. Then what we've got is a wire running between the two. Now I'm going to use this notation to show a wire coming towards us, or the current coming towards us, a circle with a dot in it. When we're dealing with electromagnetism, we've got a lot of 3D things going on. And when we're thinking of the direction that things are going in, it's good to think of an arrow or a dart. So if the dart was coming towards you, you would see a spike, a dot. So the notation is a circle with a dot in it. If it's coming in the opposite direction, you would see the tail feathers, which look like a cross. So our notations are a circle with a dot when it's towards you, and a circle with a cross when it's away from you. So in this diagram here, I've got the current coming towards us. Now when we think about the magnetic field of that current, we saw last time we'd use our right hand grip rule to show which way the field lines go around. So they're going to be going anti-clockwise around this wire. So I'm going to draw them on in concentric lines. So anti-clockwise Draw another one here. Now what's happening? At the bottom, below the wire, the magnetic field lines are running in the same direction and they're combining. But at the top, they're basically moving in opposite directions, cancelling each other out. So we can rub out our field lines at the top and we end up with this strong field underneath. I'm just going to tidy up my diagram and show that a little bit more clearly. So we now have a field pattern that looks a bit like this, where the field at the top has cancelled each other out and we've got this strengthening of field lines underneath. We can think of our field lines a bit like elastic bands. They're exerting a force, they're stretched, and they're going to want to sort of snap up and shorten, and so they exert an upward force on that wire there. So this is what we saw when we had the foil in between the two magnets and it was forced upwards. When we think about the rolling rod, it was going to be in this arrangement, so the force was horizontal, either that way or that way. Now, we don't want to be considering field lines every time we think about which direction the force is going to be. So we can use a simplification. This is where we can use our Fleming's left-hand rule to help work out the relationship between the force, current and field directions. So if we think of F for forefinger, that shows F for field, our permanent field, in this case running from north to south here. Remember, our field lines always go north to south. Now we've got the centre finger represents our current. This is coming towards us, sticking up here. So C for current, C for centre finger. And then our thumb shows the motion pushing upwards. Some students might think it easier to remember the letters FBI, which are the symbols that we use. F for force, B for the magnetic field strength, showing with the direction of the field, and I for current. So FBI, the Federal Bureau of Investigation, and also Fleming's left-hand rule.
Okay, so as Eleanor has just pointed out, sometimes it can be quite difficult for children to sort of understand two-dimensional drawings of this kind of situation. So just an idea here which might help children to grasp what is going on and Fleming's left-hand rule a little bit more clearly. Instead of sticking with two-dimensional drawings, you could try a three-dimensional model like this, fairly easily made out of two pieces of perspex with kebab skewers running between them. I've labelled north and south and used the notation of a circle with a dot or a circle with a cross to show which way the field lines are running, from north to south, with the pointed end of my skewers showing the direction of the field. Now with a model like this, children can see it from all different angles. They can stand around and view it from all different perspectives. And if we then want to talk about our Fleming's left-hand rule, we can use a piece of wire, which we've got to imagine would be connected to a full circuit. So we need to imagine we have a battery and a wire leading to here and a wire completing the circuit, so that we have a current going from positive to negative in that direction. When that is placed in the field like that, we can then use our Fleming's left-hand rule to see which way the force, or as I've labelled it, the thrust, would actually be happening. And if I used a model like this in the classroom, then I would have the children all around and they could all be using their left-hand rule to work this out. And they can see it, as I say, from different angles. So my field is coming towards you. My current, in fact, is going that way to your right. And so my thumb is now pointing down, showing the direction of the thrust. It's just a simple idea that just helps children get over the conceptual difficulties of trying to look at a two-dimensional diagram. A slightly simpler version of that is simply to make a little tool like this, and quite possibly the children could make their own. To make that, you simply need to imagine making a cube out of cardboard and then effectively cut this out of the corner of a cube. And you could use something like that in the demonstration that Eleanor showed you of the rolling wire, when you want to work out which way the wire is going to go, because I can simply sit that on top, so I can have my field going up, my current going that way, which shows me that the wire would be moving to your left.
So we've seen when we have an electromagnet and a permanent magnet, their fields can push against each other and create a force. What we want though is some continuous motion. One of the easiest ways to show this is with a homopolar motor. In this, we're using as our permanent field these neodymium magnets, where the poles are on the flat surfaces of them. I'm using a battery as my power supply, a simple cell, and what I'm going to do is make a circuit by touching the wire on the top and to the bottom, and then you can see we're getting the magnet to spin around really quite quickly. So really nice little demonstration to show that continuous motion caused by the motor effect. There are lots of ways you can arrange homopolar magnets. In this one I've got a large battery sat on the neodymium magnets there. I've got a bare bit of wire at the top and a bare bit of wire at the bottom, so the current is flowing through the wire there, and again we're getting that lovely circular motion. There are lots of different designs for these simple motors. In this one we've got more of a coil of wire, and when we connect this we're getting the spinning effect as well, again with the neodymium magnets providing the permanent magnetic field. In this case we're using our power supply as the energy source, and we can see it spinning around here. In this case we're increasing the effect because we've got lots of turns of wire in the coil. This means the magnetic field of the coil is much larger than it is if we just had one single bit of wire like we saw before. So if we had a coil of wire in a magnetic field like this model, where the current was coming round in this direction, we can see by Fleming's left-hand rule the direction of the force on this side of the coil and this side. So our field is going north to south. On this side our current is coming towards you, so the force on this side is going to be downwards. However, on this side, field's still going the same way, current's coming towards me, force is upwards. That's going to cause the coil to tip like that. However, if it carries on tipping and turns over, we've now got the current reversed on each side. So it's now being forced up on this side and down on this side. So what we need to have is some sort of mechanism where the current is always flowing in this direction at this side of the magnet and always flowing in this direction on this side of the magnet. We're going to see on a real motor how we might achieve that.
Okay, so Eleanor has just explained one problem that we seem to have with the motor, that if we're not careful it could turn through half a circle and then try to reverse. There is another problem, of course, in that if something is spinning we don't want all the wires to tangle up, so we've got a connection problem as well. We've got here a commercially produced model motor. Let's have a look at how some of those problems are solved. Before we do, let's just have a look at it running. Quite noisy, but quite powerful. Okay, the clever bit all happens just here, where some spring-loaded contacts connect to the coil. The spring-loaded contacts simply brush against two half circles of copper. With the coil in one position, the current comes through the positive and comes in on the north side of the magnet, around the coil, and leaves through the contact on the south side of the magnet. The contacts are called brushes because they simply brush against the copper connection plates. When the coil turns through half a loop, it is now the other side of the coil which becomes connected to the positive. Another way of looking at that is to say that the current always comes in on the north side and always leaves on the south side, no matter which side of the coil it's connected to, and that will make sure that it always turns in the same direction. Okay, so we've talked a lot so far about motors and about producing continual rotation, but it doesn't have to be rotation. Let's have a look at loudspeakers and how they work. I've got here a very simple model loudspeaker made out of a plastic cup. On the back I've got a cardboard cone, and I've wrapped around it about 100 turns of thin copper wire. Now it's worth pointing out just a little bit about this copper wire first of all. When you buy it like this, it looks as though it's bare copper wire, but in fact it's got a coating on it which acts as a layer of insulation. It means that when you come to connect it, you'll need a little bit of sandpaper just to clean off the coating so that you can make an electrical connection on the end there. What we're going to do is to take music from the laptop here and play it through the earphone connection through a little amplifier, and then feed the signal into the coil. The signal coming from the laptop will have the current moving backwards and forwards in time with the music. The amplifier will amplify that a little bit bigger, so now we have a large current going backwards and forwards in time with the music, and when that passes around our coil, that will become an electromagnet with a north at one end, a south at the other, but then those polarities will swap over as the current keeps reversing, so the magnetic field will reverse in time with the original music. So we've got our electromagnetic field. What we then need to do to produce some motion is to introduce our permanent magnetic field from this little stack of magnets into the coil at the back. As the magnetic field reverses, that should shake the end of the plastic cup and reproduce our music. Let's give it a go. Turn the amplifier on and start the music. Let's see what we get. And as I'm holding it, I can actually feel the cup pulling backwards and forwards. Okay, it probably isn't going to win any hi-fi awards, but it's not bad sound for a plastic cup. That's a great little demonstration that you can do, and it would be perfectly possible for your class to make their own versions of this. Here's an alternative way of connecting it, just by using the top of a 2-litre bottle and wrapping a coil of wire just around the end. And for classes to make, that's probably a slightly simpler version. If you're thinking, well, that's all well and good, but I'm not so sure we have an amplifier, there is a fair chance that you actually have got an amplifier in your physics department as part of its signal generator. Usually one half of the signal generator is an amplifier that you can connect an external signal to. So you may well have all you need to be able to make your own loudspeakers.
So in this video, we've seen how combining a permanent magnetic field with an electromagnetic field, we can produce motion and make things spin, and we can also produce sound. It's really worth emphasising to your students how integral this electromagnetism is in their lives. Just get them to think about the number of times in the last 24 hours they've used different items that contain an electric motor or contain loudspeakers. They might be shocked when they realise how common these things are in their everyday lives.